Okay, we didn't learn it, but at least we could guess what is the global minimum. Global minimum is the lowest one over structure here. This is a global minimum, right? And then we can say this is a local minimum, right? And or intermediate. And intermediate to attention state 같은 표현하고 있네. 그랬었지? This is a chair formation, and this was a boat, right? This was a twisted boat, and this was a hot chair, right? Then it's obvious. So this is a transition state. Boat is unstable because this collision everywhere. Here, everywhere is colliding 1-3 positions. So twisted boat is to avoid that conflict, to avoid that strain a little. So that's why this is intermediate, this is a transition state. Okay. Okay, that should be tertiary butyl is the strongest, this telecandrous one. I tried to explain, but it was not clear maybe to some of you. If there is a methyl, so there is some strain, this methyl to this hydrogen. If it is ethyl, it increased a little but not very much because still it has space, it goes to this direction. If it is propyl, isopropyl, then still there is an option of put this bulky one behind and then put the hydrogen in. So similar things for the sec butyl. Sec butyl is one more here. Still there is room that can escape from this conflict, right? But once it is a tertiary butyl, then no other options. This will collide with this. So that's why 4 point something range all of a sudden jump up to 11 kilojoules per mole. It's the dangerous, right? That's why comparing to isopropyl, sec butyl, iodo, this one shift that equilibrium much quicker to this direction. The other one, this direction, right? So that's why we call this locking or anchoring kind of term we use. 이건 더 미리한데. cis 1, 2. cis. 이상합니다. cis. Both of them are up. And the other one is down here, the other one is down here. Okay. So cis, what did I say? Bromo. One axial, one equatorial. If it's a flip over, then this becomes axial, this becomes equatorial. Then what could be? Two equivalent state. Energetically two equivalent state. Correct? 1 to cis. I will repeat this experiment several more times. So summarize using this chance. 1 to cis. Same 1 to cis. It should be equivalent, right? There's no difference between AE and EA energetically. Molecular position is different, but energetically it's identical, equivalent. Okay, now move to 1, 3. Okay, 1, 3 position means this one and this one. So 1, 2, 3, both of them equatorial. Equatorial is more stable, and then the other position should be here and here. If we convert axial. So that's why that should have two different isomer state, EE versus AA. And these are not resonance, right? These are all equilibrium because atom is moving, nucleus is moving. Resonance is only for electron is moving, is resonance. Any positional changes of a nucleus, any direction, okay? So that is equilibrium. Now trans one form. Okay, very good. So this should have equatorial, EE or AA, two different states. So 1, 2, 1, 4 is similar, 1, 3 is different, right? Because it is alternatively comes. The relationship of axial, equatorial is alternatively comes. So 1, 2, 1, 4 is similar, 1, 3 is different. Okay, now let's just say 정리가 됐다고 치고 glucose is the most stable one and it has all positions equatorial. That's glucose. 안 믿어져? 그려줄까? all positions are equatorial. 문맥으로 봐서 저게 답이겠지. In the textbook, last time we said mannose has actually here 2 position, galactose has this position. So that's why glucose is most common, most stable carbohydrate. Galactose, mannose is maybe next, the most abundant and next stable to isomes. Okay. Okay. Based on this, let's move on. Today we're going to stereochemistry. Okay, so far we have drawn all the chemical structures on the plane. But the carbon center has a tetrahedral structure, which is a 3-dimensional, that make extra complex situations. So now if you put something in front of a mirror, we can have a mirror image, right? So anything, we can generate a mirror image. Now we can realize that if we have the glove, so we have a left-handed glove, right-handed glove, and right-handed glove does not match with the left-hand hand, right? So there is some non-equivalent situations here. So this is what we are talking about in chemistry, stereochemistry. Stereo means it's a 3-dimensional problem. So this event that we can see in nature too, maybe this is also a mirror image, where we can say these two are the identical, but if I am upside down, it's not identical, right? So this is original image, and this is what I change it upside down. You can see some differences here, and also angle is not perfectly the matching to this because our eye is watching a little above here. That's why it looks a little unnatural. Anyway, those mirror images, if you look at any molecules, we can generate a mirror image like this. But now if you see this, let's say chloromethane, halomethane, then if you make mirror image like this, now this molecule and this molecule, if you rotate through this bond, it can be, you can recognize that those two are the same molecules, identical molecules. Right? In this situation, 2 of them is different, and then 2 of them are identical. Still, if you rotate this, then you can match with this, and these two are also identical. Now here, if all over 4 is different, if you make a mirror image, then any direction you rotate, they do not overlap. Really? This is one example of 4 structure is different. Now, 1 hydroxyl, 1 carboxylate, 1 methyl, this is lactic acid. 젖산. 운동하고 나면 막 아프게 된다는 젖산. 근육이 아픈. This lactic acid, if you make this mirror image, those 2, they do not overlap. Which direction you turn, it doesn't matter. So let's say hydrogen, oxygen, same direction, and then the other 2 does not match. If you rotate back, and then carboxylate and methyl group on the same side, now the other 2 doesn't match. So these 2 molecules seems like this is in the relationship of one hand, left hand, and right hand situations. So this event we call, this is chirality, chiral. Now, how to distinguish whether one molecule is chiral or not? This cup, if you make the mirror image, they overlap. And this hand cannot, and we can judge this if there is any internal symmetry plane. Cup case, if you put this mirror in the middle here, then left side, right side is identical, right? So internal mirror plane or internal symmetry plane, if that exists, then the molecule is not chiral. Our hand, if we divide like this, then this side and this side is not identical. If you find by rotating this, somehow you can find that symmetry plane, then that would be the non-chiral. But if you cannot find that, then it will be chiral. So let's think. My body, if I stand like this, am I chiral? Am I chiral or achiral? Non-chiral molecule we say by putting A, achiral means it has mirror plane. Okay? Am I chiral or achiral? 대충 그냥 시메트리 하다 하죠. So this is achiral. Okay? If I put like this, is this chiral? This is not chiral. If this is a fixed bond, if you rotate freely, then yes, you can say this is a chiral. But if it is a fixed, then my mirror plane here does not make same structure. Okay? One is down, one is up. So by putting this, the analogy, any structures we have, this bottle here, is this chiral? Chiral? This is achiral. Okay, 정확히 하자, 정확히. You can put mirror plane in the middle, right? Symmetry plane, achiral. You know the letters written here. This mouse, it's a achiral, but if you look at this side, it's an achiral. Right? There is a small button here, then it's not chiral. So any materials around us, you can define whether those are the chiral or achiral. Okay. Now, in chemical structures, those chirality comes from common center, which has a 4 substituent. And if there are any symmetry plane like this, and then we call this is achiral. If one carbon has 4 different substituents, then that position generates that chirality. That's why this carbon, the carbon which has 4 different substituents, that is what we call chirality center. That name is quite confusing over the history, so has changed many times. When I was a student, that was called as chiral center, and then somebody suggested that this some the limitation or difficulties to explain some other phenomena. So let's call it stereogenic center. Kind of keep changing. So I checked the textbook. Now they are calling this chirality center. Chirality center means which has a potential to be chiral. That does not mean that chirality center existence does not guarantee that the molecule is chiral. Okay. It has potential to be chiral. So that center we call chirality center. Then by looking at this structure, this is a decane, 10 carbon, 5 bromodecane. If you look at here, this position, 5 position, 1, 2, 3, 4, 5 position, 5 bromo, that position is a chirality center. Other than that, there is no chirality center. Okay. So based on this, now if you look at this molecule, is this molecule chiral or achiral? This is achiral because you can put symmetry plane in the middle here. This was drawn in the line like this, but actually one is coming out, one is coming behind. Right? Which one is which, we don't know by using this notation. But at least by looking at this structure, you can say this molecule is achiral. Now this molecule, this position is not changed, but environment is changed. Right? Once this is changed, then this carbon, left side, right side, is not identical. That's why that carbon becomes chirality center. Okay, you need a little practice, but that's not very difficult. And then by looking at this molecule, among those carbons, the chirality center, this position, now it's not drawn here, but there is a one hydrogen here, right? So one hydrogen here and 1, 2, 3 position are all different. So this is a chirality center. Chirality center can be multiple in one molecule, like this. Here, this position, one hydrogen here, 1, 2, 3 structure. This position, one methyl, this side, this side, this side, all different. And this one too. This one, this one, this one hydrogen. So these are all chirality center. 어디가 쉽지? Okay, move on. Now, how is this found? If the molecule is chiral, left hand, right hand, then what makes the difference? Left hand, right hand, if you draw my hand, it looks like almost the same. Chemically speaking, it's almost the same. Any of those, the mirror image molecules. But if it goes into the space means usually when we analyze the material, 99%, maybe 90%, let's say, we use something to analyze or to study the material. What do we use? If we have something unknown material and we wanted to characterize the material. When I was a very young student, we had something like in a can, you put those material in and shake and then hear the sound or to break it and whether it's broken or not, and watching the shape kind of things. Most of those times we use light, electromagnetic wave to analyze the materials with a different wavelengths of electromagnetic wave. Now, one way of watching of those materials is using polarized light. So our light, at least we know what is light. Yerim, what is light? 앞에부터 빨리 얘기하고 목도 아프고 말하기 힘들어. 빨리 얘기해줘. 지수가, 강지석. 지수가 해놨어. 지금, 강지금. What is light? 이 정도 민사고에서 다 배우고 오는 거 아니야? 상민이.
네.
광자의 흐름 또는 전자기파. 하나는 입자론적으로 본 거고 하나는 파동으로 본 거야, 그지? So let's take the wave, the shape first. So electromagnetic wave. It's a transverse the light, a transverse wave, not like this way. Okay, so it has up and down. X, Y is changing and moving. Okay, that's why we can collect only one direction by putting this kind of a filter, so-called a polarizer. And we can make this light into this axis, remove all others. So then this light we call polarized light. If it goes into symmetric space, then they can just go keeping this shape. Electromagnetic wave, the light is composed of electric field and magnetic field. In material, in molecule, so again, chemistry is the study of molecule, and inside the molecule, which one we study? Mainly the electrons. Right? Electron has electric charge. That's why it can have electric field. Now, molecule meets with the light, then they interact. Same interaction, we know. Same charges, they repel each other. Opposite charge, they attract each other. So molecule is here. I need one molecule. 도와줘. Come in. Make yourself achiral first. Okay, achiral. So achiral molecule here. Now this light comes through. and this is matching with this symmetry plane. Okay, if it's the same symmetry plane, make it perfect. So moving like this, then it doesn't have any difference from left and right side. That's why this motion does not change, it just passes through like this. And still same directions. Okay. Now let's make it chiral. So make it chiral. This is fine. Make it chiral. Now this light goes in and out. Let's say using make this way, that may be easier. So moving this, and then interaction between left and right, now it's different. When I had positive charge, this one is negative charge, now attracted to this. This one has nothing here, there's no interaction here. That's why in this direction, this light is more attractive to this direction. That's why this angle is changed like this. And I meet another molecule, it keeps changing. The other side, it doesn't have that motif, so just passes through. Now if I have an opposite molecule, now this symmetry changes. Comparing to the other molecule, this is exactly opposite. Now that interaction goes in, has opposite effect only here. Originally it was moving like this, then this side is moving like this. Because of this effect, interaction of electromagnetic waves, electric part first, electric field part, is interacting with the molecule's environment. That environment is an electron's environment. That part is changing and systematically only to one direction. So that is what they found, saying as optical activity. Light can be polarized. Polarized means it's a kind of a selected, moved to one direction. Which direction? Originally the light has mixture of every direction. But that light can be selected only to north and south, not west and east. This one is also we call polarized to one direction. And that light has effect with this different interaction, and then it changes the passes one way or the other way. So this is what was found even 2 centuries ago, 19th century. Those are the time the scientists was not stupid. Maybe they were more smart than us because they had limited tools, but they need to think more and more. And then they found these observations and then gave the name as optical activity or optical rotations. And using this light, now they found that some molecules, it changed that angle to the right side. Some molecules, they change that angle to the left side. Some molecules, no changes. No changes, now we can understand that those should be a chiral molecule. Right? Changing molecule is chiral molecule. And to define that one, so we don't know whether this one or this one, right? And then we need to distinguish them. That's why those molecules, they started to give extra name. So far we had 1-2 position and system trans kind of notation we gave. Now we need another notation. One molecule is a dextro. Dextro means moving right direction or clockwise direction. And level is the other side, counterclockwise directions. 2 different directions. Now we need to give one molecule has the same chemical structure, same molecular formula, but one has the activity of moving right, moving left. Then we need to give this extra information there too. Interestingly, those molecules were found. The first description of this molecule is found from tartrate. This is a tartrate molecule, and at the moment, the famous biologist Pasteur found that when he had this material and tried to crystallize, and he has very good eyes maybe, but looking at that crystal, seems like those crystals has almost the same shape, but looks like it's a mirror image. Not every molecule like this. If you have a mixture of two partner, two mirror image molecule. If you make crystal, in many cases they combine the together, left hand, right hand, matching together and make crystal like this. Okay? But in this case, only right hand molecule they are collected together, or left hand molecule they collected in an opposite way, and then they form these two different shape of a crystal. To observe this, of course, you need to have very keen eyes, right? And by observing under the microscope, and he could take one by one this shape and this shape, whatever he gave the name, let's just say right hand and left hand, and he picked up one by one. And he measured these optical rotations using this machine. And then, even at the moment, structure of this tartrate was not known. Whether carbon has tetrahedral structure or not, that's not known either. Benzene structure was not known either. Still, he could get molecular formula of the experimental formula of this, and then these optical rotations, and then gave the concept of there's some mirror image and symmetry, and these two relationship, maybe he coined maybe new term, is enantiomer. Enantiomer is two mirror image molecules which are not identical. Chemical property, physical property almost the same. Only difference we can observe is under polarized light, the interaction is in a space, the interaction is different. That relationship what he found. And then suggest something totally unmaterialized the knowledge. He's still suggested that there may be some symmetry issue in the molecules. There may be some symmetry of left-handed and right-handed may exist. It took more than 25 years. The first the chiral molecule was actually discovered and identified. So using this concept, and then this is applied to molecular structure, so-called configuration. So far we have learned the conformation, right? Conformation is at room temperature, the single bond is rotating, and it's changing with eclipsed form, staggered form. This is a conformation, we said. And then this change is a conformational change. That's why those isomers we call conformer. Right? Now, this configuration means it's the same connection, but all four motifs are different, let's just say. And then we now know that this is a chirality center. And then this position, this molecule and this mirror image molecules are enantiomer. They are not same. And dextro level is a one way, but that's experimental value. That means you need to make the molecule and then measure. And if you don't find that recorded in the table, still you cannot distinguish which one is which. So scientists or chemists needed to have a more systematic way to give the name rather than D or L. And then the measurement, what I measured was I said 10. You measured 9. And which one is the correct number? You need to measure again. So that's very cumbersome. It's very difficult to give a systematic name. That's why they tried to assign the naming of this molecule and this molecule. How will you do it? So far we had a 1,2 position, 1,3 position, cis trans kind of naming we gave, right? But by applying all those, there's no way these two molecules to assign. So that's why they tried to make some new systems to give priority all of those four and give the high number and low number. So far we have seen alphabetical order is one way, but alphabetical order may not be easy to be applied sometimes. So they gave this system. High atomic number, and that has a high priority. Okay. Then by looking at the periodic table, we have only a little more than 100 the elements, 118. So by reading those, higher atomic number has higher priority. If they have the same atomic number, Now, molecular weight, the atomic weight. Atomic number first, and then atomic weight. Means atomic number is the same, then what is the same? Electron number is the same. Or nucleus proton number is the same. That is the most important in chemistry, right? Proton number, electron number defines the chemical property of that atom. So that's why atomic number first. If they overlap, now you count neutron number. So neutron number higher, the heavier one has a higher priority. So this, utilizing this one, now we can give the relative, the priority. Now let's compare this one to this. If the first one is the same, but different, then that's easy. But if the first one is the same, carbon, carbon, now we count the next one, right? Similar way, when we gave the numbering, the system. So here, carbon, two hydrogen same, but this one is connected to hydrogen. The next one is, this one is connected to carbon. Then carbon is higher than hydrogen, so this means. Make sense? If first atom is same, then you count connected the second atom. Okay? Now here, compare this one to this one. 뭐라 그래? 어디 가지 말고 좀 뭐라 그래? Now here, oxygen, hydrogen, oxygen, carbon. Then carbon is higher than hydrogen. So this is higher number. Okay? Here, this carbon has a two carbon, and this one has one carbon. Then same carbon you ignore. Now this one is also same. Now you compare carbon to hydrogen. So using this, you can give the higher priority to this. Okay? This one. Now carbon. Now when you need to choose, then you choose the highest, the priority one first. If this is the case, carbon was the same. That's why you compare the next one. Here, carbon comparing to carbon, nitrogen is higher, so you compare nitrogen to chloride. Okay, the highest one first. Then chloride is bigger and higher number, so chloride wins. So by using these notations, and you select the higher priority one. Now, if this is connected here, first one is a carbon, and then if it has a double bond, then you consider this as two oxygen is connected. Okay, makes sense? Now here, if this is connected like this, two CC bond, then assuming that this one has a one carbon and the other carbon. And one is just a carbon and the other is connected to this part. Imaginary. Okay. To give the which one is a higher priority. Here, triple bond, you assume that it has three carbon connecting. Okay, using this, now once you give that higher the priority order 1, 2, 3, 4, then now 1, 2, 3, 4 on tetrahedral structure, and then you put lowest one behind, 4 behind, and then you draw the line 1, 2, 3 this way. In this case, this is 1, 2, 3 this way. Now we can see one is clockwise, the other is anti-clockwise. Right? In experiment, we gave the name as D as clockwise, L as anti-clockwise, but this is not experimental values. This is just by looking at that relative position, which is what we call configuration. On that carbon center, how that is positioned in space, that is a configuration. And here, if it is R, this is R, the right direction is in Latin word, the rectus is right. And left direction is sinister. So that's why if it goes to this right angle, then we call R configuration. If it goes anti-clockwise, we call S configuration. then R and D, they should be matching. D molecule is always R, or L molecule is always S. Sometimes they do, but in many cases they don't. It's a totally two different systems. So even for same molecule, you can give DR together or DS together, because RS system is by putting those priority. This priority is a kind of a random arbitrary assignment, right? By reading atomic number, we gave the priority. That's why RS system and then DL system does not need to be matching. In many cases they are matching, that's why they put that the pairing, but there is many exceptions. So those two are totally independent two systems. And by the way, this is the Latin word. We have right hand and left hand. Right hand is right and good kind of meaning it has. It's right. Left means it's kind of left over, and original meaning here, if you look at, leftus is correct, straightforward. Sinister. Sin means it's something crime related. So this is bad kind of meaning is there. In our language also same thing. 오른손. It's a right hand, right? 오른손. 왼 means it's a 그른손. So that kind of the right hand, also the left, the meaning is in almost every cultures. So this hand somehow this is used as correct one, right one. This one is something wrong or left over one. Maybe just because right-handed people is more the higher popularity. That's why this is more common. So that's why the minority is suppressed maybe. Anyway, that is the hidden in every culture. Anyway, this configuration it goes this way. All remember that number 4 should be behind, and then you make this rotation. Okay, let's practice. Now this molecule using this. Don't look at this. Using this, can you put 1, 2, 3, 4? Oxygen, CO bond, CH3. Oxygen should be number 1. You are comparing oxygen to carbon. Okay, number 1. Now this one to this one. This carbon is connected to oxygen. So this is number 2. This is number 3. Okay. If you put this hydrogen behind, then here 1, 2, 3 is moving this way. It's an I configuration. Okay, practice with this. Same thing, but this is enantiomer to each other, mirror image. And by looking at this, you should be able to draw this one, this one, this one, 1, 2, 3, rotating this way. This is the S configuration. You need to practice. So this RS notation is another example. Here again, H go behind. Try to read. So here 1, 2, 3. Can you get it? So oxygen number 1, carbon. Then you count connected the oxygen number. This is the carbon to 2 oxygen, right? This is 1 oxygen. This is 2. 1, 2, 3, and then rotate. That's up. That's the S. Here, nitrogen, carbon, nitrogen number 1, CO, CH. So this should be number 2. Okay, 1, 2, 3. Can you make that angle? Goes this way. That's also S. Experimentally, this S is minus. This S is a plus. So that's why this one has, it doesn't say here, but if you put this experimental one, you can put here D. Here you can put L. So RS system and DL system is independent. Okay, so this one is what we call configuration. Now, can you say this is R or S? R이야. R이니 S니? 연결해서. 정배가 이건 뭐야? If it's difficult to put the 4 behind, then you can put this your side and then make the rotation and then convert it. That's another way. 윤기 마음 정했어? 어이씨 금방 안 되나 봐. 지석, 강지석. 오늘 지석이 정말 안 왔나 봐. 정빈이 마음 정했니? R인 것 같아? So let's look at this. 1, 2, 3, and this is coming this side, right? Not behind. Then rotation this way. This is the S direction. Then this should be opposite. That should be up. Okay. This one, 4 is here. 1, 2, 3. We can rotate it this way. So that's also R. Okay. 연습이 좀 필요해. 혼자 볼 때마다 들여다보면서 연습하는 게 필요해. Okay, this was enantiomer. Now, based on this, we move to a little more complicated situation. If there is a molecule as mirror image, and if they are not identical, we can give DL or RS system, and we can designate them. We define that configuration. Now, how about this molecule? This molecule and this molecule, and if you look at them, this is mirror image, and then can you give now the numbering first? Which one is the number 1? This is number 1. 1, 2, 3, 4. We didn't learn this yet, but anyway, let's count. 1, 2, 3, 4, and 2 position. Is that R or S? Number the system wise, this is number 1, and CO2 and C carbon, this is number 2, this is number 3, and this is number 4. Okay, 1, 2, 3. And if you rotate this way, and now proton is, the hydrogen is coming out, that's why this looks like anti-clockwise, then this should be opposite, this should be out. And how about this? 3 position. Numbering wise, this is number 1, oxygen number 1. This is carbon connected to something else, carbon connected with only the hydrogen. 1, 2, 3. Rotating this way. Again, hydrogen is coming to your side. This is also R. Now, that means this molecule has 2 chirality centers. Previously, we counted only 1 chiral center molecule. Now, one molecule has a multiple chirality center. And then each positions we can give those RS. Then we give the name like this. Previously, it was only 1, that's why we give either S or R. And then experimental value plus, minus, or D or L. Okay, that's experimental number, the value. But in this case, now we have 2 chirality center. We needed to give those each positions 2R3R. It's an enantiomer of this mirror image, and that is a 2S3S. If it is 2 combinations, then this one should have RS. This one also has RS. How many total isomer can you generate? Here, RR-SS combination, but how about RS-SR? That's also possible. Actually, that's really, they exist too. Then by looking at this relationship, here this is a 2R3S. It's a mirror image. Now it's easy to just convert this into opposite 2S3R. Now this 2 is an enantiomer. This 2 is an enantiomer. How about this one and this one? I have one conformation, one configuration. How many mirror images can I generate? 2, including myself, 2. Mirror image is only 1. Whatever the mirror you use, the mirror image should be same. That means enantiomer, for one molecule's enantiomer is only the other pairs. Enantiomers are only 2 to each other. Then what's the relationship between these 2? They are not enantiomer. They are not mirror images. And this relationship we call diastereomer. Okay. Now this relationship here, then by looking at those notations, 2RSR, its enantiomer is 2S3S. Just convert this. 2S3S, 2R3R. 2R3S, 2S3R. It's easy. Now the other options here, all of these molecules comparing to this. This is a pairing of enantiomers. This is different. These are the diastereomers. And important thing here is enantiomers, they are identical to each other except the optical rotation, optical activity. Diastereomers, they are totally different molecules. Diastereomers, they have a different molecular, different melting point and boiling point, and totally different molecules. Physical property, chemical properties, all different. They are different molecules, isomers. Okay. So, if we test how many chirality center in this the steroid molecule here, can you count? Let's start here. This one, chiral or not? Chiral. This one, this is achiral because of HH. Okay, 2 of them is the same, then it doesn't count. Chirality center should have 4 different motifs, right? How about this position? 1, 2, 3, they are all different. This is chiral. And this one. This is also chiral because it looks, first one looks like same, but if you go the other direction, they are different. So this is also chirality center. This one is also chirality center. This one is also chirality center. And this one, chirality center. This one, yes. This one, yes. This one, even that one is a yes. There are many. This one is not. Because this CH3, this CH3 is identical. This one, this side is different, right? That's why this is chirality center, but this is not. How many chirality center here? 9? If it's 9, then how many isomers do they have? 2 to the 9th. A lot. 2 to the 10 is a 1024. 2 to the 9th is a 512. 500 stereoisomers that they have. So there are many, right? There are many. Now, if among those, only one position is opposite, one S and the other one is R, then that's diastereomer, one kind of diastereomer, but specifically, the special name they give, epimer. Quite similar, but only one stereogenic center is the opposite, is what we call epimer. Only one position is changing, we call epimerization. That configuration is changing. Okay. 시작은 쉬웠는데 뒤로 가니까 조금씩 복잡해지려고 그래. 오케이, 조금만 더 하자. This is a morphine molecule. How many chirality center here? 생각보다 많지는 않네. How many? 6. 나가서 한번 찍어볼래? 스크린 좀 낮춰줄까? 자, 세보자 같이.
일단 여기
오케이, 1, 2, 3, 4, 5,
근데 이거랑 이건 아니고
아닌 것 같네. H가 두 개가 똑같으니까. just give 한 개는 어디 갔지?
아 5개.
아, 5개인 것 같아? 5개가 두 개면 It's a 5. 연습이 조금 필요하지만 그렇게 어렵진 않아. So if you look at here, if any position with the same HH, then you don't consider. Any sp2 carbon is on the same plane, you don't count. It should be sp3 carbon, and it should have 4 different substituents. Then if you look at again, now this position here, 1, 2, you don't count this, 3, 4, and 5 here. Okay, 5 stereogenic center. Then it should have 32 isomers. Only one pair of enantiomer each. These are all stereomers. Now, come back to titrate. Titrate here, this molecule and this molecule. This is what the Pasteur used to get the enantiomer. It has also 2 stereogenic center, 2 chirality center. Then it should have 4 isomers like this. If you look at here, these 2 is what you count. 1 R form, 1 S form, and he characterized. There's another pair like this. This is enantiomer, correct? But these 2 has a little issue. If you look at this molecule, if you look at those substituents, oxygen, the hydroxyl, carboxylate, hydrogen. Hydroxyl, carboxylate, hydrogen. It's identical, right? Now, if you rotate this one 180 degree this way, this molecule and this molecule is identical. Originally, it was a mirror image. 2s, 3r, 2r, 3s. It should be an enantiomer relationship. But this molecule, if you rotate it, then it's identical. Means this is not chiral. How do you define it? By looking at that whether the molecule has internal symmetry plane inside. If symmetry plane is there, that means the mirror image should be same molecule, right? So now we encountered new situation that even though one molecule has 2 chirality center, still if there is mirror plane, symmetry plane in the middle, then those molecule is not chiral, and those are identical molecule. That kind of a relationship or that kind of molecule is kind of a 2 molecule is originally should have 4 isomer, but two of them is identical. That molecule we call meso compound. Meso compound has chirality center inside, but at the same time it has mirror plane. That's why altogether the molecule is not chiral. 어디 보자. 잠깐 좀 나와볼래? 저 나오라 그래. 잠깐 좀 나와봐. 도움이 필요해. 자, 아티클 로테이션 한 번 더 해보자. 자. Okay. Now let's say this position, 수직. Okay, thank you. This position is now chiral. this position, chirality center. This position is also chirality center. If you have only half of this molecule is perfectly chiral. Now it has mirror plane in the middle, symmetry plane. Now polarized light comes in. Polarized light comes in, and then it interacts with the left side and right side. It's cancelled out. Okay, this side I tilted a little this way, but go this way, they tilt down this way. So it's cancelled out. Each part is chiral, but if it's combined together with symmetry plane in the middle, and this light goes in and then move like this, but eventually it's cancelled out. That's why this molecule is not chiral. Okay, that is the situation of a meso compound. So by looking at this structure, if you put this molecule, these three molecules, positive molecule has, of course, plus value, -1 minus value, and meso molecule, of course, it doesn't have optical rotations. Because altogether, because of that internal symmetry here, okay, because of this internal symmetry, the molecule overall is not chiral. So this molecule is what we call meso molecule. What do you think? Is this molecule chiral or not? Cyclobutane 1,2,6 is this molecule chiral or not? This molecule has internal symmetry plane in the middle, right? So this molecule is meso. If I say trans 1,2, what do you think? Trans 1,2 is a chiral, and it should have this and this. Right? It should have one pair of enantiomer there, and it should be chiral. Okay. Now next class. Okay, let's practice a little more. This is the last page of today. This molecule, chiral one. You can find the symmetry plane here, right? This is chiral center, chiral center. Now if I ask you, what is this, the configuration, R or S? This position? It's R. 연습은 각자 하고. This molecule has a mirror plane here. That's why achiral. How about this? Chiral or chiral? Now, if you have this axis goes down, this axis goes up, right? If you have this axis here, if you rotate 180 degrees, it's the same molecule, isn't it? Yes, that's true, but that is not related to this chirality. You don't count it. That's rotational symmetry operation, but rotational symmetry we don't count. We count only mirror symmetry. Okay, so this molecule is chiral. Okay, don't be confused. We say only symmetry mirror plane. If that exists here, achiral, this one is a chiral. That means its enantiomer is here right now, up, down. This enantiomer should be down, up. Okay, that's enantiomer. How about this? This molecule, if you put the symmetry plane here, it goes here, right? So this should be chiral. This is not symmetric, that's why chiral. Symmetry plane, best one you can draw this way. Right? How about this? You need to rotate to fit to make the chiral plane. Is that chiral or not? If you rotate this into here, then hydrogen goes down bromine, bromide goes up.
아카이소.
This compound has a middle plane here. Not clear? Then you need to practice. Then you do. Okay? So to summarize what we have learned today. Carbon has a tetrahedral structure. That's spatial positioning. Right? That spatial positioning we call configuration. And there is chance of a mirror image is not identical. And those relationship we call enantiomer. Physical property, chemical property almost identical. Melting point and everything is exactly the same. Only difference is when it meets with the light, polarized light, that interaction is different in space. So one way it moves to this way, the other way it moves to this way. How much it moves it depending on the molecule, but anyway it has a chance to move to one direction. That position of a carbon we call chirality center. Chirality center is only one, then you have only one pair of enantiomer. Now chirality center is more than one. Now the isomer number increase 2 to the n. Okay. Now, even though there is more than one chirality center, if there is internal mirror plane, then that molecule is not chiral. Those kind of molecule we call mesocompound. Okay. Right-handed, left-handed is averaged out, then total effect is the same. That's what it means. 자, 처음 배우는 거면 요거 컨피그레이션 RS 맞추는 것도 연습이 필요한 일이고 숙제에 조건 좀 숙제는 벌써 내놨어. 그래서 숙제 미리 할 사람 숙제 미리 해도 되는데 연습이 필요한 거 RS는 어떤 구조를 주더라도 다 그릴 수 있어야 돼. 이걸 바탕으로 다음 주에는 좀 더 복잡한 얘기를 다음 시간에 좀 더 복잡한 얘기를 할 테니까 모듈러 수업도 있잖아요, 그지? 여기서는 좀 더 복잡한 얘기를 할 거예요. 그걸 이해하려면 지금 이 기본을 잘 이해를 해야 다음 수업을 들을 수가 있어요. 오케이? 따로 얘기 안 해도 적당한 수준의 복습과 복습만 해보세요. 오케이? 수업 여기까지.